This is found in your Teams taskbar, usually at the top. And they will be answered during the Q&A section of the webinar. Commonly, I might actually just leave that up there for a little bit, make sure everyone knows what they're doing before just skipping across. Wonderful. Okay, so that should be plenty of time. Commonly asked questions. Slides and video recording will be received within the next business days. Please monitor your junk inbox. Then, regarding the certificate of attendance, we will provide the link just prior to the Q&A section.
Jasmine, sorry to disturb you, but your slide is not moving.
Oh no!
You're still on. Yeah, it's still stuck in slide number 3.
Yep. So we're meant to be in slide number 3 still because we're going through the certificate of attendance.
No, I thought you said certificate of attendance. Okay. Yep. No problem.
Yep. Which, gosh, we have quite a number of wonderful people here today, which is amazing. Alrighty. So, as mentioned, these certificates will be sent within the next 4 business days. Please note that weekends are not inclusive of those business days. About EIT. So EIT, the Engineering Institute of Technology, exists to bring engineers and engineering-minded people together. As one of the few institutions in the world focused solely on engineering, EIT offers both vocational and higher education programs accredited by the Australian government, with many also recognised under the 3 international engineering accords, which is pretty amazing. Our lecturers are industry experts, such as Professor Kalam, and programs are designed to ensure graduates gain cutting-edge practical skills. EIT's unique delivery model is centred on student success. It's really giving you all you need. So both ECT and ECST are dedicated to delivering just bear with me, world-class education, as the same with EIT. ECT and ECST are located, there's one in South Africa and one in the UK, which is super exciting. So just bear with me one moment, please. This disclaimer is pretty important. So, the courses and qualifications mentioned in this presentation are offered by separate legal entities operating in different jurisdictions, one in Australia, one in South Africa, and one in the United Kingdom. Each entity is subject to its own local regulatory body and requirements and accreditation standards. Prospective students should refer to the relevant institution's official website for accurate, up-to-date information specific to their location, including course availability, fees, regulatory status, and enrollment conditions. Now, I will send you all a link to each individual website. Code of conduct. Please keep discussions lawful and respectful. Follow the moderator's directions and do not share illegal, abusive content. Not that you guys would do that, but, Anyways, I will be welcoming Professor Kalam. This is the Mysteries Earth fault that didn't return to Earth. Please take control.
Right. Thank you very much, Jasmine. I'm taking control. Right. Um, can all of you see my slide? I'm in slide number 8, which talks about mysteries. Jasmine, can you see it, please?
I
Jasmine, you're
sure
muted.
can.
Okay, good. Good day to everyone, and thank you very much for coming to this presentation today. In fact, this is a very interesting one because, as all of you know, that when there is an earth fault, the earth fault should actually return to the earth. This case, it did not return to the earth. So this is a great mystery. And the great mystery because this challenges one of the most and most deeply ingrained assumptions in power engineering. That is, we all know from the beginning that if there's an earth fault, it goes through the earth. That's all we know. And we know that, right? But this one did not. And any protection engineer will tell you that it kept them baffled. And let us try and see what happened. Now, before telling about myself, a bit about myself, I would like to ensure that you understand what we are trying to do. First of all, this is not, I repeat, this is not a traditional technical presentation. This, to me, is a storytelling. Lullaby, baby, that type, you know. I'm telling you a story. The only difference is that I don't want you to go to sleep. This is very much something that I love. I always wanted to become Sherlock Holmes in my life. I wanted to become a detective. I wanted to become a forensic scientist. I still remember when I was in England, we used to have these forensic science type of drama. Doctor Who was there. Those type of character. You know, those 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 ones who seem to be very crazy but very intelligent. I'm neither one of them. Neither intelligent, neither good looking too. I want to be like the Pink Panther. You might have heard about the Pink Panther, Inspector Jack Clouseau. I want to be like that. You know, that's exactly how Peter Sellers was. I want to become Inspector Colombo, not Inspector, Lieutenant Colombo. Lieutenant Colombo. That's Peter Falk. And as I told you, I always wanted to become Sherlock Holmes. I don't know why the hell did I get and become a stupid academic. So, this is my way of taking revenge and actually becoming what I should have been doing all my life. So, it is not a traditional technical lecture that you're used to. It's a different thing. It will be a lot of action, a lot of fibs that I'll be telling you about, and a lot of corrections I'll be making, and why these mysteries occurred. As far as I'm concerned, I am a emeritus professor at Victoria University and at EIT, and I've got a few other jobs that I do. I'm also editor in chief of Australian Journal of Electrical and Electronic Engineering. Published number of papers. It seems that after looking at that it seems that I do nothing but publish papers. Okay, believe me. To me, the mysteries are more important than all the papers and the PhD students that I've produced and the DN student that I've produced. Things like change management plan, challenge is always something that I love. Qualification, I've got my PhD from University of Bath, uh, my master's from, which is from Bath is in England, and master's from Oklahoma, which is in the United States. And I did my initial studies in India. I've got professional membership of most of the organizations that you can think of. Now, today's presentation, I'd like to know, and I want you to understand what I'm going to cover. And my first thing is always why you want to study these mysteries. And then I'll introduce the case. I'll talk about some hypotheses. I'll talk about fundamentals and how I resolved this problem. The problem was there and I resolved it. And then I'll give you some key technical issues, give you a bit of knowledge or gyan, as we call it, takeaways. And there'll be opportunities for question and answer. So, my friends, my case is that why am I studying these mysteries? Why am I doing this? Very simple. You will understand. Always the problems start very small and then it gets big. Any problem that always starts small and then it becomes big. One thing is for sure, real systems rarely fail. The other thing is that engineers are called when data is incomplete. And I hate to admit this. Sorry about this. I hate to admit this. But what you learn in textbooks is not what you practice in actual life. A textbook is an ideal condition, but in actual life, you will find the situation will be quite different. And that is where your experience comes in. That's exactly where that structured intuition, which is in the form of experience, that comes in. And the experience is the one which will get you to solve any issues. And that's what I'm trying to teach. I'm trying to teach you, or I'm trying to train you to be able to be a forensic scientist. I want you to understand that try and go deep into it. I want to make it funny also because I hate myself. I hate boring lectures. I hate it. Okay? I don't want you to go to sleep. That's why you will see. I will shout. I will beg. I will cajole. I'll wake you up. Right? So now you might ask, what is this mystery in engineering? Why? Everyone thinks engineering is a very structured area. Everything is known. You've got all these textbooks, you've got all these papers, you've got all these publications, got all these PhDs, you've got all these DA, you've got all these masters, you've got all these bachelors. Why? What makes a mystery in engineering? And the reason is very simple. The whole behavior is intermittent. I'll give you one example today. We're talking about renewable energy. Did you know no one can predict when the sun is going to come out, whether it's going to be enough temperature, whether the rain is going to fall, whether it's going to be a cyclone, whether it's going to. You can work in the meteorological offices and try and find out with the science, but the behavior is intermittent. But one thing good about it is that the symptoms are time dependent. So if you look at it, many times the root cause is non-electrical. And you'll be surprised, my friends, many times the problem in engineering is you and me who are the engineers. It is not the machine which is the problem. It is you and me. We human are masking the reality. So these mysteries emerge when our mental model of the system is wrong. Not the mental model, not the system, the mental model. Not when the equipment is necessarily faulty. It is we who are part of it, and that's the beauty of it. So, what defines an engineering mystery? You have got systems, you've got no alarms. The nature of behavior is intermittent or time dependent. The data is conflicting. And assumptions, you can have multiple plausible assumptions. So, right in the beginning, I'm telling you that the mysteries that we have is exposing my weakness, my 50 years of engineering experience weakness. This is what it is. So, this mystery is exposing me to it. And the next thing is that why? Why this is a true mystery? And if you ask any engineering person, anyone, even a techo, the earth fault, they say, is a very simple matter. We all know, and if you don't know, please know from now, the protection schemes for any such type of faults or abnormalities in the system are very well established. So there's nothing wrong, right? The system, the scheme is established, relays are there, measurements can be done, but still the relays fail. And the measurement that came out is not what I expected. And that is a fault. Like, to give you examples, we have overcurrent protection. Since the time of Adam, we have had overcurrent protection. Nothing new about it, my friend. Adam and Eve knew about the protection of the earth fault protection and overcurrent protection, differential protection. It's been there for donkey years. Then, as I said, if you ask any engineer, every engineer would say that we are very confident when there is an earth fault. We know that we can solve this issue. And that overconfidence of an engineer is dangerous. It's not the system, it is not anything of that sort, but that overconfidence that we can solve this issue is dangerous. And I'll show you. So, you might have the best protection scheme in the world, the system failed. It failed because it failed to operate. It gave contradictory measurements. All these were purely because now we are talking about the modern power systems. We are not talking about the system which was 50, 60, 100 years back. We're talking about the modern power systems. We're talking about environmental factors. And we are talking about infrastructure, which is very aging. Most of your infrastructure that you have is 50 years of age, 40 years of age. On the top of that, we say that the scheme is established. The environment that these schemes have been exposed to has evolved. You know that everyone now uses PV. So you've got inverters. We all talk about DG, distributed generation. We all talk about a lot of things that are coming new into the system, which is rendering the traditional setting which we have put that machine to invalid. And what is the reason for such failure? What is the reason for such type of failures? And I'll give you a few one. The first one I want to do, the first one I want to do is talk about the measurements. What I want to talk about is measurements. And the measurements that I want to talk about is what was contradicting the expectation. The first device I want to talk about is instrument transformer. That is CTs and VTs, current transformers and voltage transformers. You know, saturation can occur. If you have got high currents, faults, the CTs are overwhelmed, it produces inaccurate, reduce the signal saturation. If the relay sees a small current then actually exists, it does not trip. It's expecting a large current. Because of the saturation effect, the relay is seeing something smaller and it does not trip. Then, in that measurements, I can have issues with magnetism, especially remnant magnetism. You will find that the residual magnetism in the core of an instrument transformer can cause it to saturate faster than expected, especially in a faulty condition. And therefore, you get erratic measurement. The third thing I can think of is environmental impact on line parameters. You know that temperature can change. And if there is, for argument's sake, in a place where you are staying, if the temperature changes, say by 10 degrees Celsius, so the line temperature has increased by 10 degrees Celsius, your wire resistance will increase by 4%. It will create measurement errors of up to 48% depending on the soil conductivity. The fourth thing in this particular measurements area I can mention is the topologies, which is the uncalculated system topology. So from passive network, you're going to active network. That is, now you've got inverters, distributed generation, and they are all going to impact and alter your fault current. Therefore, your standard pre-calculated setting becomes ineffective. So that's all on measurements part. The second concept that I want to talk about is the failure to operate. That means your relay has misoperated. There could be errors in logic and design. There could be setting which is inconsistent. You have done commissioning which is wrong. The contact failures, especially if it's an electromagnetic relays, the contact failures can be a problem. The DC system could be at fault. All that can happen in the relay itself. Then the environmental factor, the physical and environmental factor. You've got components. I told you most of the components, go to the power system, you see most of the components over there has aged substantially. We're not using the new component, we're using something 50 years back. The contact might have degraded. There might be EMI effect, electromagnetic interference. There could be contamination. So, my friends, you need to have some sort of mitigation strategies. And the mitigation strategies, I think, is to have current detectors so that you know whether the current has gone up or low. commission to improve, modernization, modernize your system, and you have some sort of compensating device so that it can bring the temperature down to room temperature. So this is why all my system that was such a simple system that we have learned in the textbook has failed. So let us go back to my study that I have started and look at my system that I have. Let me look at this. And I've got a simple system, my friend, a medium voltage industrial distribution system where there's a generation, there's transmission line, there's a load, all that stuff. It has multiple feeders. The equipment frames are solidly earthed. The numerical protection relays are pretty modern. So I don't think there's anything exotic that I'm talking about. This is a standard industrial medium voltage system. And this has been designed, my friend, this has been designed to the best practice. So, in order to go forward with this, let us try and see what is the problem. The problem is very simple. If you look at that diagram, my friends, if you look at that diagram, there's a fault over there. Can you see that red fault? It's a phase to earth fault. Look at it. It's A phase to earth fault. Look, that is A phase, that is B phase, that is C phase. So it's A phase to earth fault. There will be a visible arc damage, but the earth fault relay did not trip. And the system kept on operating. In spite of having that fault, my friend, the system operating. So, in fact, the fault was there. Electrically, it was faulted. The system behaved as if nothing happened. That could be very dangerous, my friend. It could be fatal too. This is the problem that is there, right? So, and what I would do and look at it carefully, putting my hat as Lieutenant Colombo, I would first think of safety. I want to be safe. I do all the things of hazard that I have got. I do the touch voltage risk. I look at equipment damage. I look at if there's any fire coming from there. I look at if there's any protection credibility. My friend, this is not a technical curiosity. This is a serious safety issue, a very serious one. Now, all of you who've done undergraduate qualification in engineering, you know what you want to see. Okay. And as I told you, I already have a mental model of my system. And we all have that. And it's going to bring misunderstanding to whatever we are doing. We are expecting to see fault current, which is going to flow through the earth. This is what we are expecting. Return is via ground grid or soil. We expect that there will be a residual current and we can detect it. We expect that the relay will trip. Now, let me tell you what the measurements actually saw and what the measurements actually showed. It showed very little residual current, no neutral displacement. The relay did not pick up and there was no fault evidence. This is actually the case. The fault is there, the relay did not pick up. So your measurement that you've got has contradicted the physical reality observed on the site. You see, that's what you were expecting. You were expecting the relay to pick up. You expected that there would be some sort of visible thing. You expected there would be some sort of neutral displacement. You expected that there would be some residual current, but everything was different than what you have learned up till now. Everything was contradicting. Therefore, as a as someone which is Inspector Jack Clouseau, I come to some sort of hypothesis. And first thing I do, relay is the failure. The brain, which is the relay, that is a failure. So I do the setting check. Then I looked at the polarity of the CTs. I did some injection tests. It passed. I looked at it, the relay. Relay is functioning properly. I was expecting to see something like that. It was perfectly fine. Right, my friends? The protection hardware was innocent. Nothing wrong with that. And because of that, my whole concept of relay being the problem that failed and the mystery deepened. I went and started talking to few of my colleagues and tried to find out what actually happened. So I think I solved the problem because people said to me, it's a high resistance fault. High resistance fault. If you know, this is what is called zone 1 and zone 2. The fault, because the resistance was high, the fault resistance, it went to zone 2 and therefore it did not operate in zone 1 time. So you think that there is a fault resistance which is a problem. You think that there is contamination on the surface that you are looking at, you are examining, and that's a problem. You think that the arc mark indicated that there is low impedance. You think all these things, and all your hypotheses have been rejected. My friends, these were not a weak or marginal fault. This should have been obviously an electrical issue. So, therefore, I think that I would like to revisit the question. And therefore, I want to go back to the studies that I have made and ask these four questions. What is Earth electrically? And before I talk about that, I'm giving you a philosophical turn to this whole thing and try and look at philosophy. Electrically, Earth is massive conductive and relatively neutral reservoir of charge that acts as zero voltage. That's why we call it reference point. It is generally treated as a sink that can accept or provide unlimited electrons without significantly changing its own charge, often used for grounding or to enhance safety. So the question that I asked, my first question that I've asked is, what is Earth electrically? Earth electrically is zero voltage or the reference value. That means the voltage over there is zero, and that's a standard reference point. Conductive resistance, it is not as conductive as copper. The earth is conductor that can absorb massive amount of charges, such as from lightning, or provide a low resistance path for fault currents. And just to give you a bit more example of what is earth ground with versus circuit ground, earth ground refers to actual dirt per soil, while circuit ground is common return path within a device. So that is what is earth. My next question is earth always part of the circuit? Normally, I would have asked you all these questions, but that will make my lecture 3 hours long. That's why I'm giving you the answers. No, Earth is generally not a part of a normally operating circuit. It is just a safety system. In normal operation, electricity flows from the source through the load, that is the appliance, and back to the neutral wire to the source. It does not go through the dirt. The fault condition is such: if a hot wire touches a metal casing, the protective earth wire carries the current to the ground, allowing the circuit breakers to trip. The exceptions? In certain rural areas, in particular in Australia, I don't know about your part of the world, but we do use what we call sway lines. Sway lines is single wire earth return. Jasmine was laughing. She thought I was talking about some dirty word that I was going to use. No, I'm not going to use that. I haven't gone stooped down to that level up till now, Jasmine. It is called sway line, single wire earth return. Okay. And or it could be HVDC, high voltage DC system. The earth itself is used as the return conductor. So it is not a part of the normal operating circuit. Now, the third question I've got: does current require salt? Sorry, does current require soil? No, 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 no. Current does not require salt to flow. Current requires a closed loop to flow. Continuously, it will flow through that loop. While soil is a conductor that can complete this loop, metal wires, neutrals are more efficient. My last question: where does current close its loop? In normal operation, the current closes its loop at the source of the power, that is, at the distribution transformer, traveling back through the neutral conductor. If there is a ground fault, like in our case, there was a phase to earth fault, A phase to earth fault. If a device is grounded, the loop for a fault current is hot wire. It could be metal case, it could be ground wire, it could be main panel, it could be transformer, it could be anything that I can think of. Okay? Or it could be direct to earth. If there's a live wire which touches the literal dirt, the current spreads out and travels through the earth back to the ground at the local transformer. So, my friend, in summary, what I want to tell you: earth is just a safety system, not a return path. And this is what your textbook has been telling you. It is wrong. It is not a return path. It is for everyday electrical use, though it acts as a universal reference for voltage. The voltage reference value is zero. So let me see some insight into this. And the first thing that I come back to is that current has to return back to its source. Earth is not a source. Earth is not magic, my friend. Earth is just another conductor. No magic over here. Abracadabra, I'm not doing anything of that sort. Abracadabra, nothing of that sort. It's just another conductor. So my friends, What I'm seeing now is the grounding method of the system, not of individual component of the system. The system neutral has to be isolated from Earth. There is no neutral earthing resistor. There is no grounding transformer. It's a floating system by design. And that's what I'm talking about. The system was intentionally ungrounded, something many engineers forget after commissioning. Many of them forget it. Now, if it is an ungrounded system, what is happening? What happens in the ungrounded system? Current is very low, minimal current. My relay did not trip. Fault current is via capacitors. Look at that. It's going to the capacitance. There's no solid return path. The system continues operating, and the fault which is there has not been detected by your protection relay. Very simple. QED, problem solved. The behavior is normal, my friend, but it was not up to your expectation. Yes, that is true. It was not up to your expectation, but it did behave exactly the way it was supposed to behave, right? It did behave exactly the way it was supposed to behave. So let us think about the return path. And this is what it is. I've drawn all that circuit. I've shown you how the phase to earth capacitance is there, how the cable capacitances are there, how the motor winding capacitance are there, how it is distributed, not concentrated. The fault current did return, but it did not go through the soil. That is the hidden truth. There was, there was a return path, but it did not come through the soil. So what the relay saw, as a matter of fact, what the relay saw was nothing. And that's exactly what the relay did not see anything. The capacitive current was very small. The balance across phases was not there. Okay, the residual sum was near zero. The relay saw everything below sensitivity, it did not operate. And this is classical high resistance fault. So this protective relay failed to detect this single line to ground fault, and this is a challenge which is faced by electrical power systems on a daily basis. Typically, stemming from the fault characteristic not meeting the relay's threshold. The relay may see nothing because the fault current is too low. You can't blame the relay. The system grounding is ineffective or the fault is intermittent. And as I mentioned, it is because this is the high resistance fault. It could be because of system grounding configuration, could be about relay setting and sensitivity, could be due to technical and physical limitations, and all that sort of thing. So now my question is that why the damage still occurred? There was damage, my friend. And look at that. This is what actually happens. My friends, look at this. This is the beauty. Okay, this actually happens. It sees. Sorry, did I go further? Yep, yeah, this is the one. Um, Capacitive current was very small, so the relay did not see anything. I told it in the beginning. I said everything was balanced, no problem. Sum of residual was zero, there was no problem, and sensitivity of relay was it was below that, so it did not operate. That's exactly what happened. It saw nothing, it did not operate. Then why the damage still occurred? Why the damage still occurred? Because look at that. There's the initial transient current. Initially, it goes very high, 3 to 4 times the steady state value. Local arc energy is sufficient. Mechanical and thermal damage can be done, and the steady state current is still very, very small. That's a steady state value. So, transient effect can cause real damage. By the way, the transient effect is for a very short period of time, very high value. And this can actually cause damage even when the steady state system value looks harmless. So now, the moment of realization. Let me try it and realize fault did not return to Earth. It returned to the source. Earth was just hosting the contact, and the mental model had to be corrected. This is the moment that you will remember years later what I'm telling you today. Years later, you'll remember that I told you that fault does not return to the earth. It went back to the source. Earth was just the contact. And then my next thing is why? Why this is often misunderstood? Why? That is because of the way we do symbol writing. Look at that. These are the five major elements: fire, air, water, earth, etc. Okay? Uh, and this is the symbol. It looks very similar. Earth, earth, which is there, which is here. If you look at that, in the earth, it implies a sink. The language gives you the misconception. And academics want to use simple teaching method not to confuse student, and they gave you wrong information. This is a rare exposure to ungrounded system. So symbols shape thinking, and many times we as engineers are often mistaken and misled with these symbols. So now the correct protection philosophy should be that we have got monitoring devices on the insulation. We have got detection of the neutral displacement. We have got grounding transformers, and we have got clear grounding strategies. If you have got that, you can't get wrong. Protection must match the grounding philosophy, or it will not work. In this case, it did not match, and therefore it did not work. So, how the issue was resolved? Something someone might ask. Install the grounding transformer. Define your neutral earth reference. Increase the earth fault current intentionally. Have reliable detection. And this is where you will find that having these earthing transformers, which is the grounding transformer that I'm talking about, addresses the non-detection of ground faults, especially in underground, ungrounded system, or the what I call the high impedance grounded electrical faults, such as delta connected network. So if you have that, you can do that. You can solve this problem. It's a very dangerous half truth I want to talk about. And it's very interesting. You see that there's a bird on the tower or bird on the transmission line. Nothing happens to that bird. But when that person is there, when you're sitting and you're touching the ground, you get a hell of a shock. Most probably will die. But remember, earth faults are safer in ungrounded system. It is definitely true for continuity. It is false for insulation stress, and it is false for fault location. Look at that Simple bird, say a miner sitting on the truck, nothing happened to that bird because there is no earth connection. So we have got such type of similar world issues, and some of them I'll be picking it up. One is mines with floating network, ships and offshore platform, data centers with IT system, hospital with isolated supplies. These are across the industry. Such type of operation is happening, and please remember that you, you who are the early career people, have to understand and have to understand this very clearly, that how to resolve such type of issue. And again, I would have asked you this question, and I'm running short of time. And Jasmine is telling me, giving me this timeout signal. And therefore, I want to hurry it up. What happens if the second, after the first ground fault, earth fault, a second one came? If it came, okay, it will have insulation failure, there will be short circuit conditions, and there will be system disruption. Where does current flow then? Okay, the current will flow to the path, it will have a magnitude, and what protection operates? Overcurrent protection will operate. The ground relay, if it's there, will operate, and the directional relay, if it's there, it will operate. How fast must we act? If we don't act fast, the whole system might disappear. So, my friend, what is the lesson that we have learned? What is the lesson we have learned? Earth is not a current sink. And grounding defines the fault behavior. Protection flows physics, not symbols. We think symbols is going to solve the problem. No, always trace the return path. This lesson applies to all type of earth faults, whatever fault is there. So why this mystery persists? Because you cannot demonstrate it experimentally. You can't do the behavior check. Overconfidence when you knew that you know the solution and you don't have any documentation on grounding. Most of the time, you learn about Earth in your second year, and most of the time, you forget it. And often that is where the problem occurs. So, the deeper engineering truth which is there, my friends, the deeper engineering truth which is there, system behaved exactly as it was built. It was not imagined, it was not labeled, it was not assumed. Okay, system behaved exactly as it was designed. On reflection, on reflection, what I want to mention is that would you, as a junior engineer, early career researcher, be able to solve this? What experience was critical? What type of knowledge you required? How could you improve the detection, or how could you improve the procedures for improving the detection? And that is something that you have to reflect about. And as a closing thought, I want to mention, I want to mention that not all problems, my friend, announce themselves electrically. They don't say, "We are coming." Okay, Mr. Novako, be careful, I'm coming. It will not do like that. Some speak to sound, some speak to time, some speaks to behavior. So remember, these are not formulas, my friend. And the key takeaway that I can take from all this, the key takeaway that I can take from all this, not all faults are failures. There are time, there are time patterns that matter. Network behavior matters the most. Investigation is the best thing. Don't assume anything. So remember, right in the beginning, I told you, earth faults are, we consider it very simple. We know protection system is there. We know everything is perfect, but still relays did not operate. It's still, my measurement was not as I expected. Remember again, my friends, Earth fault don't give a damn about symbol. They don't care about the symbol. They care about the circuits. So you can see I've drawn some fault path current so that you can understand that. They don't care what symbols I use. With that, I've completed my presentation. Thank you very much for listening to this presentation. Just wanted to end with one or one or two things, and that is I've got my next mystery seminar. Mysteries one next to is the 9th of April and 16th of April. The 9th of April is when the solar inverter that wouldn't sink at noon, and the 16th April when lightning didn't strike, but the surge arresters blew. Another two mysteries in engineering. Another two mysteries in engineering. With that, I've completed my presentation. And Jasmine, all up to you. I'm sorry, I've just gone 2 minutes beyond time. But still, if you want, we can continue with the question and answer for a few more minutes. Thank you very much, everyone.
I think we'll need to. I'll take control. But we'll
Yes, please.
certainly
Yes,
get through
please.
these questions. There's some questions in the Q&A section. So if you just click that Q&A button at the top of your taskbar, it should open that for you.
Louis has asked a question: how does a grounding transformer help in limiting fault current and improving system protection during ground fault? That is the whole purpose of a ground transformer, Louis, is to make sure that it is grounded in the system. Therefore, it has protected it completely. That's why it is essential that we have some sort of grounding. Even if nothing is there, some sort of reactors or Peterson coils is what was used in the olden days. You can use that. Then again, Lewis continues with his comments. Is it possible to harvest or recover usable electricity from the earth? And what are the scientific and practical limitations of this concept? In theory, you can do that. In practical, I think it is very difficult. I'm talking about the amount of electricity that comes is minuscule, and therefore it is. I believe that there is a practical limitation. I would like and understand an issue. Again, Louis continues with the third one. Man, Louis, you want to have a private tuition, I think. Okay. Uh, I would like to understand the issue. What condition can cause an earth fault current to take an unintended path instead of returning directly to Earth? I've given you that example in my mystery example itself. This was a classical thing when the system was ungrounded and it failed. How do residual current devices, RCDs, detect? Just a minute. Oh, I lost. Yeah, RCD detect leakage current and protect against electrical. RCDs are exactly very similar. It's like a reactor or a resistor which is in the system. It detects the current because V is equal to IR, and it finds that, and automatically it protects against shock if that is an in-between buffer media which is there. What are the standard protection schemes used for detecting fault in electrical? Differential protection, distance protection, you name it, it's all there. And I can go through the whole list, gamut of it. But you can find that in my textbook or any book that you can find. Um, uh, then the last question is completely different. Okay, it is the format and structure of writing a scientific article could be done. The answer is no. The answer is definitely no, because uh, any journal, they have got their own structure and format. You have to follow their pattern. You can't do your own, or else your paper, however good it would be, would not be accepted because you do not follow the pattern of the formatting that they have asked you to. You can't do things of your own accord. The journal is particular, specifically designed for that purpose. I hope, Louise, I've answered all your questions.
There
Any other
are
question?
some additional questions if you scroll all the way back up to the top. 2 more have
Oh,
been
sorry.
added. No, that's not you. They've just added it just now.
I can't. There's nothing in there.
Nothing from.
You read it. You read it.
Absolutely. So the first one is, does it mean that a PEN system is subjected to having more earth faults?
Could be.
Okay.
The answer is could be.
How does
Okay. What is the second one?
How does current flow back to the source if the system is undergrounded? How does
Because the loop, I showed you the loop. Okay. Then there was 1 or 2 more questions, which I don't know where that questions are coming and going, because I can only see Luis's one. I love
That's all.
Luis.
That concludes the questions, I believe. Thank you, everyone. So, thank you, everyone, and thank you, Professor Kalam. I really appreciate everyone's time today. On the screen, you'll see our upcoming courses. You can see that we have quite a few in April, then a few, one in May, and then a few in June, which is very exciting. That's obviously for EIT. Then we've got our ECT, so we've got a few coming up. Not for quite some time, but they're in the process. And then you've got the ECST that's coming up in August. It's very, very exciting. The time that everyone has been waiting for, and more than understandably so. On the screen, you'll see the QR code. I will provide you with links as well, and my very personal email in case anyone needs anything course related. I'm more than happy to assist wherever I can. There we are. It was an incredible webinar. On the screen now, you'll see many different ways of contacting the different colleges, which is very critical and crucial. You'll also see the links that I've provided to the individual websites in case you have any interest. This will conclude our webinar today. Thank you all very, very much. I'll stop the recording.
Thank you very much. And thank you very much, Jasmine, for your help and your emceeing the whole
Thank you so much
webinar.
for your time.
You take care and have a great day. Bye-bye.
Likewise. Thank you. See you.